Imagine the universe, everything you see, everything you are, is part of a grand, cosmic dance. It's a dance of energy, of motion, of heat. Thermodynamics is the story of that dance. It's the science that describes how energy moves and changes. From the fiery heart of a distant star to the quiet hum of your refrigerator, it's the rule book for everything that happens, everywhere. Why does a hot cup of coffee cool down? Why can't we build a machine that runs forever? The answers are written in the language of thermodynamics, a language that governs the destiny of the cosmos and the details of our daily lives. Long before we had a name for it, our ancestors were keenly aware of its power. For most of human history, our power was limited. It came from our own muscles, from the muscles of domesticated animals, or from the gentle push of wind and water. Our world was small, and our ambitions were tethered to these natural limits. Then, something extraordinary happened. We learned to harness the power of heat itself. We learned to turn water into steam and use its incredible expansive force to do work. This wasn't just a new invention, it was the birth of a new age. The Industrial Revolution was ignited not just by coal, but by a revolutionary idea, that heat could be converted into motion. The first steam engines were clunky, inefficient beasts. Early pioneers like Thomas Savery and Thomas Newcomen developed engines primarily to pump water out of flooded coal mines. They were a brute force solution to a pressing problem. But they worked. They showed that the steam created by boiling water could be put to work, replacing the labor of hundreds of horses. These early engines were like the first clumsy land animals crawling out of the sea, awkward, but representing a monumental leap forward in evolution. They were the harbingers of a world remade by mechanical power, a world where human potential was no longer bound by muscle. As steam engines multiplied, a new kind of scientist emerged, eager to understand the principles behind them. They wanted to know, how can we build better, more efficient engines? This practical question led to profound discoveries about the universe itself. The first great rule they uncovered is now known as the first law of thermodynamics. You might know it by another name, the conservation of energy. Energy cannot be created or destroyed. It can only change its form. Chemical energy in a lump of coal becomes heat energy in the boiler, becomes the kinetic energy of the moving piston which turns the wheels of the train. The total amount of energy in the universe is constant. It just keeps moving around, changing costumes in the cosmic play. But if energy is never lost, why do engines need more fuel? Why does a ball eventually stop rolling? This brings us to the second law of thermodynamics. The second law introduces us to a concept called entropy. You can think of entropy as a measure of disorder or randomness. The law states that in any energy conversion, the total entropy of a closed system will always increase over time. Things naturally go from order to disorder. It gives time a direction. It's the arrow of time. The story of thermodynamics isn't just about abstract laws, it's a human story, populated by brilliant individuals who piece together this grand puzzle. We've already met James Watt, the practical genius who perfected the steam engine and in doing so, set the stage for the theoretical questions that would follow. His work created the very machines that scientists would later study to uncover the rules of energy. He was the engineer who built the laboratory, even if he didn't know it, for a new generation of physicists. One of the first to truly tackle the why was a young French military engineer named Sadi Carnot. In his only published work, Reflections on the Motive Power of Fire, he analyzed the steam engine not as a complex machine of pistons and gears, but as an idealized heat engine. He realized that the key to an engine's work wasn't just about creating heat, but about the flow of heat from a hot place to a cold place. Carnot's work laid the conceptual foundation for the second law. He showed that there is a fundamental limit to the efficiency of any heat engine, a limit dictated by the temperatures it operates between. Later, the German physicist Rudolf Clausius picked up where Carnot left off. It was Clausius who formally stated the first and second laws of thermodynamics in their mathematical form. More importantly, he gave a name to the mysterious quantity that always seemed to increase. He called it entropy. He famously summarized the first two laws in a beautifully concise statement: the energy of the universe is constant, the entropy of the universe tends to a maximum. And then there was William Thomson, later known as Lord Kelvin, a towering figure in 19th century science. Kelvin's contributions were immense. He helped unify the seemingly disparate fields of heat, electricity, and magnetism into a coherent theory of energy. He proposed the absolute temperature scale, now named the Kelvin scale in his honor, which begins at the coldest possible point, absolute zero. These pioneers, and many others, were the architects who built the magnificent structure of thermodynamics, a science that would forever change our view of the universe. The laws these pioneers discovered are not relics of the steam age. They are everywhere, silently and powerfully shaping our world every single moment. Look around you. The device you are using to read this, your computer, your smartphone, is a marvel of thermodynamic engineering. Its microchips generate immense heat, and tiny fans or heat sinks, designed using principles of heat transfer, work constantly to carry that waste heat away, preventing the delicate circuits from melting. Every time you charge its battery, you are witnessing the first law in action, converting electrical energy into stored chemical energy. The fact that the battery gets warm while charging is a direct consequence of the second law's unavoidable tax of entropy. Think about your daily life. The refrigerator in your kitchen is a heat engine running in reverse. It uses energy to pump heat from a cold place, inside the fridge, to a warmer place. Your kitchen, the car you drive, is a modern heat engine, far more complex than Watt's but governed by the very same laws of efficiency that Carnot described. Even life itself is a thermodynamic battle. Your body is an incredibly complex system that maintains a state of low entropy, a state of intricate order, by constantly consuming energy from food and releasing waste heat into the environment. The reach of thermodynamics extends far beyond our planet. It is the key to understanding the cosmos. A star is a gigantic fusion reactor, a cosmic power plant governed by the balance between the outward pressure from the heat of nuclear reactions and the inward pull of gravity. The very structure and evolution of the entire universe, from the initial moments after the Big Bang to its ultimate fate, is a story told in the language of thermodynamics. The story of thermodynamics is the story of our universe's operating system, and a wise species is one that learns to read the manual.